In this video, we're going to be talking about binary search trees. So before we get into it, let's review maps. So we learned about maps, and we know that they have very fast lookup, and they do that by using keys. Keys have to be unique, but maps are able to take in a key and give back some value associated with that tree, and they're very fast. An example is looking up a net ID using a UIN. We are also now very familiar with the C++ standard API for maps. We know that the square bracket operators and the @ function both have lookup and insert capabilities. However, there is some special cases about how they handle lookups or accesses for keys that are not in the maps. You have to be careful about using them. You can also call insert and in place as insert functions. And better ways to look up include using functions like find and count. So we know that the great thing about maps is that they have lookup, insert, and erase capabilities that are log n worst case, which is great. So let's talk a little bit about how we can implement some of these functions inside of the map API using the data structures that we're already really familiar with. So let's look at vectors to start. So a vector or array doesn't really matter, but the idea is that what if we had a vector and it was in sorted key order and we used binary search? What would be the worst case time complexity of find for this implementation? Well, we know binary search can go to the middle of the array or vector and then split again and then split again and then split again until it finds what it's looking for. And that complexity comes down to log n, because log n is the amount of times it takes to split n by 2 until you get down to 1. Another implementation is, let's say we have a vector, but this time it's not in sorted order, it's just in random order, and so we use linear search. Well, in that case, we're going to have to walk through the entire list, array, vector until we find what we're looking for, and so that's going to be O of n. What about a linked list? Does that help us at all? So let's say we had a linked list, it was in sorted order, and what if we used binary search on that? So if it was in sorted order, we normally, in binary search, right, you find the middle element. But because it's a linked list, you don't have direct access to the middle element. So there's no way of directly going there. Instead, you're going to have to walk through the list. So let's say we have a linked list with 5 elements. Even though we know that this should be the middle element that we check, the only way to get there is to walk through the other elements in front of it. And so by the time you do that, you've already walked through half the list, and then as you keep splitting in half, you're going to end up walking through n elements in the worst case scenario. So for example, in the case of, let's say that the element we were looking at was here, we would walk through these two to get to the middle, and then once we got to the middle we would want to go here, which would require us to walk here, and then we would find we needed to go right, and then we would walk here. So you'd walk through the whole list. And then obviously a linked list that's in key order that you use linear search on is no different than using linear search on a vector, so that's also O of n. Alright, let's look at insert. So let's first start with first start with a vector in sorted order of the keys. We use binary search to find the location that you want to insert, and then we insert. So for a vector, the worst case scenario is going to be that you do a binary search and you find that you need to insert it at the front, and because it's a vector you have to shift everything over from the right to the left, and so that's going to cost O of n. So even though binary search is efficient and is able to find it, quickly or more quickly, the shifting of the elements in the data structure of a vector is going to still cost O of n. Now, if we do linear search instead of binary search and do an insert, there's no difference. The linear search is going to be of O of n, and it's also going to be O of n if you have to shift. So in worst case scenario, worst case scenario would be a couple different cases. One is the thing you're looking for is at the end of the list, then linear search would cost n. Or worst case could be that it's at the front of the list and then linear search gets you there quickly, but the shifting is going to cost O of n. A vector in key order and you add to the end and resort. So adding to the end is very inexpensive for a vector. That's constant because you know where the last element is. But then sorting is not constant, and we know that the best sort we can do is log n log n. So any of our divide and conquer sorting algorithms are n log n, which allow you to sort by splitting the list, and that's where you get the log, but then the number of elements you have to switch around, worst case, is always n. So n log n is the best we can do with sorting. The other type of sorting algorithms that we learned about are n squared, but you can do better than that. And then if we go to our linked list option, we saw that find on a linked list is always O of n, regardless of whether you use linear search or binary search. So it doesn't really matter how we search, but let's say we use linear search to find the location and then insert. In that case, the linear search is going to be O of n, but the insert actually is not expensive for us because you can just relink the members. But finding where to insert is where you get the O of n complexity. So as you can see, we are stuck with an implementation that doesn't allow us to have log n in both find and insert with vectors or linked lists. So no combination of what we just looked at will allow us to have log n find and log n insert, right? Using the same implementation. So we need to have a new data structure in order to do this. So what if we used a linked list, but we recursively folded it? So we have this sorted data in a linked list, and then we fold it in half in the middle, and then we find the middles of these new parts of the list, and we fold those in half. This builds the structure, which is maintaining the sorted order, but it's linking itself together in a more efficient way. Instead of walking linear through the list, you can see that we've shortened the distance from the first node that we access to the last node we access quite a bit, right? Log n, it's only log n now. So searching for a particular value in this type of data structure that is connected in this tree is called log of n, because what we're doing is we're taking every node and we are having two edges off of every node and two branches off of every node in below it. So what that means is if you take n nodes and you split them by 2 until you no longer have any more to split, then you are going to have a height of log n. And the way that this works out, if you're just kind of thinking about it mathematically, so we know we have n nodes, right? And when you split the nodes like this by 2 by 2 by 2 by 2, you're figuring out how many powers of 2 there are, right? So if you take 2 to the x, the question is 2 to what equals n, right? How many times do we have to raise a number to get n? How many times do you have to raise up the power, the 2 to 2 in order to get n? And then if you just do some algebra on this and take the log of both sides to get that x out, then we get x log n equals x times log of 2. And then if we solve for x, we get log of n divided by log of 2. And we know that for a big O we can ignore constants, so log 2 is just a constant. So log of n comes from how many times you have to split n by 2 before you get to 1. Right? So if you have 64, how many times do you have to split 64 until you get back to 1? Well, you know that 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, and 2 to the 6 is 64, right? So you know that it's 6 times in order to get 64 down to 1. So this is the height of the tree is log of n. That's how you get that. So searching a tree, if you just look at the arrows, you can only at most go through log n values, right? 1, 2, 1, 2, 1, 2, 1, 2. And that's the height of the tree. And same goes for insert and delete. It's the same idea. You have to search first to find where you want to insert or delete, but then once you find it, it's just a matter of rewiring. So just like a linked list, a tree has that really nice feature that insert and delete, once you find where you want to insert and delete, is really inexpensive because you're just relinking nodes. And so you also get log n complexity with insert and delete. So let's look at an example. So this is an example of the structure that we just built. And the question is, how will you insert newt? Well, one of the things that you might have noticed about this tree is that because we started the tree off when we were recursively folding it, we started it in sorted order. So one of the features of one of these trees is that whenever you go to the left of the tree's node, you're going to find values that are smaller. Whenever you go to the right of the tree's nodes, you're going to find values that are larger. And that holds recursively with the smaller subtrees. So smaller, larger, smaller, larger. So when we go to this example, we have the same thing. You can see cat is less than elephant, bear is less than cat, dog is greater than cat. We have owl, which is greater than elephant. We have moth, which is greater than owl, and ferret is less than owl, and then ferret, which is less than moth. Pig is greater than owl, zebra is greater than pig. So that is the that is a factor of starting off with it in sorted order and then folding it recursively. So where would you insert newt? What would this insert look like? We're going to go through the algorithm in a future video, but this is just to start getting you familiar with how nice it is. Well, you just go to the head node, elephant, the root node, and if newt is larger than the node, then you go right. If it's less than the node, you go left. So newt is larger than elephant, so you're going to go right. Newt is less than owl, so it's going to go left. Newt is greater than moth, and there's no child there, so you're going to add it here. So as you can see, to find where to insert took log n, and to insert was nothing, right? You just make the new node and you connect it to its parent. This structure is called a binary search tree, and it's often also called a BST. Every node has at most 2 linked subnodes, which are called children, and for every node, all the values to the left are less than its parent, and all of the values to the right are greater than its parent. And a binary search tree is a type of tree that has these additional features. So all the other things we talked about trees are also true, but there's these 2 new conditions. The first condition is that each node can only have 2 children. So a tree in general could there could be a parent could have as many children as needed, but a binary search tree specifies that there's only 2 children. And then the second feature is that all the values that descend down from a node's left side are guaranteed to be less, and its right side are guaranteed to be greater. This is a great website for visualizing and building binary search trees, so check it out if you're interested. It's really helpful in working through binary search tree algorithms and checking to make sure that your algorithms work on different trees, you also can draw them, but this is a nice visualization tool as well. One of the things we're going to be working on over the next few videos is a BST class. So here is a sample BST class of integers that we're going to call tree. And the idea of a binary search tree class is really simple member variables, just like the linked list. All you have to keep track of is the size and the root node, and then the rest of it gets taken care of in the node itself, whether that's a struct or another class. So here we have a struct, which we call node, and it has the value that it stores as well as its left and right connections. And then the private member variables are just the root and the size. And then obviously there's going to be all of the constructors and all of the member functions that allow it to do all the things that you need it to do. The interesting thing about binary search tree classes, a lot of times it's really useful to use a binary search tree for something else, like to build a map or to build a set. And so you can have lots of different abstractions, but just like with the linked list, we're going to just build a binary search tree class so you can see how it works, but know that you can build that into any abstraction. We'll go through and talk about insert, and we're going to talk about search, traversal, how to find the height, so we'll work through all of those member functions. For now, we're just going to build a default constructor that sets the root node to null and the size to 0, and then we'll let insert build the tree from there. And so the behavior of the binary search tree class is that if you insert 22, it will be the root node, and then when you insert 11, it will go here because it's to the left of 22. When you insert 49, it'll go here. And the thing to keep in mind is that binary search trees depend on the order that they were sorted, right? So insert will change the way that the tree is built depending on what order that you insert them. So if I inserted these nodes in the order of 11, 22, and 49, you'd get a different tree because the first node, 11, would be the root node. And then everything would be dependent on that. So let's check to see if we are understanding the features of a binary search tree before we start talking about some of the algorithms. So the question is this a binary search tree? And if it is not, which node is incorrectly ordered? So pause the video and think about it, and then come back when you're ready. So let's just go through and look at each node. So this is the root node, and then we'll go to the left. Sean is less than Shen, so that looks okay. Amanda is less than Sean, so that's okay. And Lei is greater than Amanda, which is okay. And we also want to make sure that Lei fits in with the rest. So Lei is also less than, the nodes above it, so it's also okay. So if we inserted Lei in the top, Lei would go left, left, and then right, so that looks right. Yanlin is greater than Shen, so that's okay, because it followed its path correctly. So that one looks good. And then Ragib is LMNOPQRS. So Ragbid is less than Yanlin, so it's correct here, but Ragib is not greater than Shen, so it shouldn't have made it down to this branch because you start from the front, right? So this one should not have gone to the right when it was inserted into the root of Shen, right? Because R is before Shen, so it should have gone this direction and found its place on the other side of the tree. So it's not a binary search tree because that element is in the wrong spot. And it's important that you have a valid binary search tree, because basically none of the algorithms work if the two conditions aren't true. So every node only has two children, and all of the nodes on the left side of a node have to be less than that node, and all of the nodes on the right side of that node have to be greater than that node. Otherwise, everything breaks down. So that's it for this introduction to binary search trees. We will be moving on to search, insert, traversal, and height of binary search trees in the next few videos.